So So 4.8, like I said, last section on linear equation systems is about the rank of a matrix, the nullity, and fundamental matrix spaces. Some of them we have already, actually, you have seen them all already. Okay, so we start again by looking at the matrix A. And again, the book makes it a little bit larger, so there are some things to see actually. So this time it's again, I guess it's 4 by 6 again. Okay, yeah. So we have 1, -3, 4, -2, 5, and 4. We have 2, -6, 9, -1, 8, and 2. We have 2, -6, 9, -1, 9, and 7. And we have -1, 3, -4, 2, -5, -4. Maybe I should also check 1, -3, 4, -2, 5, 4, 2, -6, 9, -1, 8, 2, 2, -6, 9, -1, 9, 7, -1, 3, -4, 2, -5, -4. Okay, so, and then last time we said, also last time means just in the previous section, this thing has 4 rows. So we have R1 transposed, R2 transposed, R3 transposed, R4 transposed. So this here is R4, no transposed. So the vector would be -1, 3, -4. And then we have 6 columns. So let's call this C1, C2, C3, C4, C5, and C6. So these are the column vectors, these are the row vectors. And again, the row space of A is the span of R1, R2, R3, R4, and the column space of A is the span of these columns, C1, C2, C3, C4, C5, C6. So I call it C for column, but keep in mind, so this is not a coefficient. No? C1 is a 4 vector. No? So this is a subspace of R6. This is a subspace of R4. Okay, so we have the row space and the column space. Now what we do, which is kind of funny, not really funny, but you can imagine already what we do. We take this matrix and we run the Gauss-Jordan algorithm. So we transform it to reduced row echelon form. And now I do something, because I also like to introduce variables, because later I like to reorder my columns. So I pretend I have a linear equation system AX equal to 0. But it turns out, as you will see, the 0 is not important. I only do this so I can actually give names, variable names to the columns. No? Also don't think about why I use now a homogeneous linear equation system. It's really not so important. So I'm not sure how I can do this best. Let's try to do this here. So now we essentially, what I'm doing now is think about something like solve A times X equal to 0. No? Let's pretend this would be our problem. But the main reason why I do this now, I like to do a Gauss-Jordan algorithm. So if you like, forget about the 0, that's fine, because the zeros will not change anyway. So we do Gauss-Jordan again. So we write, I make sure that I don't copy anything wrong. That's always deadly. 1, -3, 4, -2, 5, 4. And artificially I add a 0 to make this here, no? Then 2, -6, 9, -1, 8, 2, 0. 2, -6, 9, -1, 9, 7, 0. -1, 3, -4, 2, -5, -4, and 0. So that would be the augmented matrix. I hope I didn't copy something wrong. Okay, and we do Gauss-Jordan to bring it to reduced row echelon form. Okay, I make, also again, our book is nice to us. We have already a leading one, so I make zeros here, and 0 here. So -2 times row 1, -2 times row 1, plus row 1. That will already generate the zeros in the first column under the leading one. 1, -3, 4, -2, 5, 4, 0. Then this -2 times this, 0, this -2 times this, 0, this -2 times 1, yeah, so we have a leading 1 already. This -2 times this is a 3, this -2 times this is -2, this -2 times this is -6, and the zeros never change. Same thing here, this -2 times this, 0, this -2 times this, 0, this -2 times this, 1, this -2 times this, 3, this -2 times this, -1, this -2 times this, -1, 0, this plus this, 0, 0, 0, 0, 0, 0, 0. Okay, we again have right away a 0 row. And again, as I said, our book is nice to us. We have a leading 1, so we only eliminate this one and make it a 0. So we make minus row 2. We have 1, -3, 4, -2, 5, 4, 0, 0, 0, 0. That will not change anyway. 0, 0, 1, 3, -2, -6, 0, 0. Now this minus this, 0, this minus this, 0, this minus this. Wow, right away at 1. This minus this, 5. And the last row was 0 anyway. Okay, so now we have our leading ones. We see there is 3 of them. So we need to make zeros on top. So let's start from the right. So minus 5 times row 3 plus 2 times row 3. So we have 1, -3, 4, -2. Now this minus 5 times this is 0. This minus 5 times this, 4 minus 25 is how much do we have here? Sorry, what did I say? 4 minus 25 is minus 21, no? Sorry. 0, 0, 1, 3, then this plus 2 times this is 0, this plus 2 times this is 4, and then 0, 0, 0, 0, 1, 5, and 0 row. And finally, we have to eliminate this guy, minus 4 times row 2. So we have 1, minus 3, 0, minus 2, minus 12 is negative 14. This minus 0 is already 0. This minus 4 times this is negative 37. Then we have 0, 0, 1, 3, 0, 4, 0, 0, 0, 0, 1, 5, 0, 0, 0, 0, 0, 0. Okay, and Just to, now you see why I actually introduced this as a linear equation system. So I make here x1, x2, x3, x4, x5, x6, and I rearrange them. But this is only to show you this identity matrix again. Later on, we start talking about this. But here it's always kind of hidden. Why? Because the ones are mixed in. So it's actually clearer down here. So you see again the structure. So I would do here x1, x3, x5, and then the remaining ones, x2, x4, x6, and the right-hand side. So x1 is 1, 0, 0, 0. x3 is 0, 1, 0, 0. x5 is 0, 0, 1, 0. And then x2 is minus 3, 0, 0, 0. x4 is minus 14, 3, 0, 0. And x6 is minus 37, 4, 5, and 0. And again, we see, also again, like later I talk about this, but this is again to emphasize, after having the right arrangement of the columns, means have them in the right order, we have here an identity matrix, in this case 3 by 3. So these are the leading variables, 1, 3, and 5. Then here we have a block where any type of number can be in there. Then we have 0 rows here, and then this number, or maybe there are several of them and there are more rows, this number always determines if we are consistent or not. In this case, we have to be consistent because we have just a 0 side. But if they're non-zero, it can be non-zero number here, and that means if it's the case, it's inconsistent. Okay, so again, these are the leading 1 variables. And these are our 3 variables. Means each one of them gets a parameter. Okay, but in this case, actually, we didn't like to solve it. We only take a matrix and just do the calculation. And I only put here variables so I can show you one more time that we can always assume this is an identity part and a block part with numbers which can be arbitrary, and a right-hand side, which came from the original right-hand side. No? So this is essentially when you only look at the matrix A, or better here, before we rearrange our variables. And this comes only from, because artificially I added a right-hand side. So make it, instead of 4 by 6, I make it 4 by 7. But the 7th column is really because I turned it into a linear equation system. So we see a little bit better that there are variables going with every column. Okay, so now the main point of this section is now, and I'm sorry I used too much space for my example. It would have been good. That was actually my goal, to have everything on one page, but that doesn't work. So we have an original matrix A with a row space. And we have an original matrix A with a column space. Now we learned we can run reduced row echelon form up to here. No? Then I reshuffle columns not to see this. But let's forget about this for a moment. So this is the matrix A. And we go to this matrix, call it A tilde. No? Yeah, or can I call it capital R? I don't know. Let's call it capital R. I'm not sure if this is smart, but R stands for reduced row echelon form. No? But here the identity matrix is a little bit hidden in 3 columns. No? Okay, so this is the matrix A with a row and column space. This is a matrix R with a row and column space. Now the question is, here the row and column space is very easy to see what it is. Here it's difficult to see, but is there actually any relationship between row and column space of A and row and column space of R? It turns out there is a relationship, and The book doesn't prove it, and I actually also don't like to prove it. Even it's actually not so difficult. We have actually all tools together, because what do we do from here, 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 here? Our three operation is multiplying a row by a number, switching two rows, and adding a row to another row, no? After maybe multiplying it first. It turns out it's very easy to see when you do these three OR operations, the row space does not change. The row space here is equal to the row space here. Because for sure, if you multiply a row by number, the row space doesn't change. If you switch two rows, that doesn't change anything. It's just the order of the rows. The only thing they have to think is if you have two vectors, v1 and v2, and then we have a vector v1 and v1 plus v2, do they generate the same space? And it turns out they do. It's very easy to see. So it turns out during these operations, the row space doesn't change. So row space of R is equal to the row space of A. Where here we had these four weird vectors where we have no clue. For example, are they linear independent? For example, here it's very easy to see. It's an identity matrix. So these three vectors are linear independent, and the fourth vector you can forget because it's a zero vector. So it turns out here the row space is given by these three rows, and it turns out the row space here is the same as the row space here. So the row space has not changed, and obviously we have three linear independent row vectors. So the dimension of the row spaces here is 3. Because it has not changed, the dimension of the row space here was also 3. Okay, so that's really good. Row space of the reduced row echelon form is the same as the row space of the original matrix, and it's very easy to see a basis and therefore the dimension 3. Okay, so what about the column space? Column space is more complicated because when you look here at the columns, then obviously the last row is always 0. But here the last row is not 0. Oh, bad luck, no? Okay, so it means the column space of R is not equal to the column space of A. But again, what are we actually doing from here to here to here to here? Remember, we always can consider elementary row operations as multiplications from the left with invertible matrices. Whenever you multiply matrices from the left, vectors from the left with invertible matrices, independence stays independent. So it turns out the column space changes, but the number of linear independent vectors doesn't change. Okay, so I like to write this down. So that's maybe a lot to digest. And as I said, the proof would be actually not difficult. I give you 5 linear independent vectors, you multiply by an invertible matrix, and the question is, are these now new vectors still linear independent? And they are. And it's actually very easy to show with the invertibility of A. So there's really no secret here. I just like to skip this. So what turns out to be row space of R, row space of A are the same. Dimension of the column space of R and dimension of the column space of A are the same, but not the column spaces itself. Obviously, no, because here we have zeros, here we don't have zeros. Okay, so I like to write this down. So as a result, so row space of A is equal to row space of R. Nothing has changed with this space. And then I write dim for dimension of column space of A is equal to the dimension of the column space of R. So these are two results. As I said, they are not difficult to show. I just like to skip this. I've never done this in this class, but as I said, it would also not a big issue to show this. Actually, there's no deep secret in here. Okay, now we have this. Now we go back to our matrix R. And again, in some way, it's actually, so keep in mind, this is R. The only change here is actually I reordered the columns. And here it's now much easier to see. What is actually the dimension of the column space of R? We have 1, 0, 0, 0, 1, 0, 0, 0, 1. And the 0 is always on the bottom, but it will not change because these are 3 linear independent vectors. And obviously, these 3 vectors can be written as a linear combination of these 3. So the dimension of the column space is equal to the number of leading ones. Now, what is the dimension of the row space? First, we have these 3 vectors. Again, we have the hidden identity matrix. So these 3 row vectors are also linear independent. And the number of independent row vectors is again equal to the number of leading ones. So it turns out here this is impossible. Here this is impossible to see. Here it's very easy to see. The dimension of the row space and the dimension of the column space is always equal to the number of leading ones. Yeah, because these 3 vectors, column vectors make these 3, and we have 3 row vectors, and because of the leading ones, they are linear independent. So this is now very nice. So it turns out row space of A is equal to the row space of R. Dimension of the column space is equal to the dimension of the column space of R. And the dimension of the column space of R is actually equal to the dimension of the row space of R. And from reduced row echelon form, we see right away that the dimension of the row space of R is equal to the dimension of the column space of R. And what is always number of leading ones. And now we say, oh, but the row space is the same as the row space of R. So we can say this is equal to the dimension of the row space of A from this line. And this is equal to the dimension of the column space of A. And so if this is equal to this, this is equal to this, this is equal to this, and this is equal to the number of leading ones. And this is now kind of, okay, it's very easy to see once you think about reduced row echelon form, no? But that's kind of the secret here. If you think about this, that is something like a very surprising result. So you have here 6 columns, each 4 coordinates. You have 4 rows, each 6 coordinates. And it turns out for every matrix, it doesn't matter which matrix, the number of linear independent rows and the number of linear independent columns, which we call the dimension, are the same. So if only 3 rows are linear independent, then only 3 columns are linear independent. And you cannot make it in any different way. So the number of linear independent rows and the number of linear independent columns, even here, there are 4 here, 6 here. They always have to be the same. So if you have a 1000 times 6 matrix, no? 1000 columns, 1000 rows, 6 columns. The 1000 rows can have at most 6 independent vectors. Because whatever you do, you cannot go over the 6. No? So this is kind of an amazing result and totally unclear if you look at this matrix from the beginning, that the number of linear independent columns and the number of linear independent rows are the same. And in our example, also for this matrix, the number of leading ones is 3. So there are 3 independent rows, 3 independent columns. And from the calculation you see, because remember the row space doesn't actually change, the first 3 rows are linear independent because we didn't switch rows here. No? So you see actually the first 3 rows are the linear independent ones. Okay, so this is a lot to digest, but that's an important result. And kind of after this, that will be tomorrow. Based on this result, we now do some calculations about row space or dimension of row space, dimension of column space. And this number, this magic number here, also dimension of the row space is equal to the dimension is number of columns. This number of leading ones gets a name, and every matrix this number is determined by, you can find it by reduced to echelon form. This name is called the rank of a matrix. So the rank of a matrix is the number of independent columns, which is equal to the number of independent rows. So tomorrow I will repeat this line, say this is true for every matrix. We find this by doing reduced to echelon form, and then we introduce a name for it, which will be the rank. So, okay, so I would say tomorrow about half of section 4.8 is missing. So I start tomorrow with section 4.8 and do the remaining half. And then we cover 4.9, which is the last section in chapter 4. And also before we go to 4.9, I try to make a picture, which is hard because M and N can be big numbers, but which shows you a little bit when can we solve a linear equation system? What does it actually mean in a picture? Okay, so with this, I like to finish for today. Are there any questions about these last results? Okay. No. Yeah, I think I assigned the homework for 4.8 already, but I put the due day 1 day later. So the due day, I think, is Friday night instead of Thursday night. Also Thursday midnight is actually the due day. So I leave it on. So even you cannot do the questions, or maybe you can take a look, but the assignment is like, it will actually come tomorrow. So I made it already 1 day longer for 4.8. So tomorrow we still work on 4.8, and then also we will tomorrow finish 4.9. Okay, so if there are no more questions, then I stop the screen sharing and I finish the meeting. So, and again, 3 o'clock, if you like, we have office hours, and otherwise I will see you tomorrow.